In this video, we are going to be looking for the roots of complex numbers. And in order to do that, we are going to use de Moivre's theorem. Now, this is going to be somewhat of a different variation of de Moivre's theorem when compared to finding the powers of complex numbers. But one thing that it is still the same, and you'll notice it right here, is that de Moivre's theorem still requires us to have a complex number in polar form. You notice those trig functions c, I, sine, cosine, I, sine. That said, if you are looking for the roots of a complex number, but you are given a number in rectangular form, then you're going to want to convert that to polar form first. And we'll do an example where we have to do that in a little bit, just as a reminder. But let's go ahead and take a little bit of a closer look at what this variation of de Moivre's theorem looks like. All right, you're going to notice that it is very similar to the standard polar form, which I'm boxing right now. All right, but the thing is that we're taking some nth root of our leading coefficient r, and we're also doing something interesting inside of our trig functions where we're dividing two terms by n. And what is n? Okay, well, n is going to be the distinct number of roots that we're looking for. So if we're looking for 3 roots of a complex number, then what we're going to need to do, and what we're doing here in de Moivre's theorem, is we're going to have to take the cubed root of it. So if we're looking for 3 roots, then we're going to need to take the cubed root of it. If we're looking for 2 roots, then we're going to have to take the square root of it. If we're looking for 10 roots, we're going to have to take the 10th root of our complex number in order to get those 10 roots. All right, so that's what n is. It's however many distinct roots we're looking for. And then there's going to be another letter in here, another variable in here that you might not know. It's going to be that k, and it's going to show up both in our cosine function and our sine function. And that k is always going to start at 0. It's always going to start at 0, and it's going to go up by 1 for every root you're looking for up until you get to n minus 1. So that's always going to give you the number of roots you're looking for. So for example, if we're looking for 3 cubed roots of a complex number, then we're going to use k as 0. We're going to use k as 1, and we're going to use k as 2, and that will give us 3 roots. All right, so yes, that means we do have to calculate de Moivre's theorem 3 times if we're looking for 3 roots. But yes, we're going to have to calculate it those 3 times to get those 3 distinct roots. That said, let's go ahead and try to apply de Moivre's theorem for finding the roots of complex numbers to an example. All right, so here's a simple one. What are the 3 cube roots of the complex number 10 times cosine 165 plus I sine 165, and that's in degrees. So this is a simple one because it's already in polar form. So all we need to do is recall de Moivre's theorem for finding the roots of complex numbers, and we really just need to plug in the information we need 3 different times for our 3 cube roots. That said, let's go ahead and get started. I'm going to start off with blue, and my leading coefficient 10 here, that's going to look like the cubed root of 10 for my first root. And sorry, I'll try to write a little bit better. And then I'm going to do cosine. My original angle is 165 degrees, and I'm going to divide that by 3 because that's how many roots I'm looking for. And I'm going to add 360 degrees times 0 over 3, again, because that's how many roots I'm looking for. All right. And then plus I sine 165 degrees, the exact same thing. And I'm going to start shorthanding this to the CIS form in a minute, just so I don't have to keep writing the same thing over and over again. But that's going to be 165 degrees over 3 plus 360 degrees times 0 over 3. Now, if I want to simplify this, it's just a little bit of arithmetic inside of those trig parentheses. And that's going to simplify to the cubed root of 10 times CIS, and then what's going to be inside this, those trig function parentheses with just a little bit of math should be 55 degrees. And that's going to represent my first root. All right. Sure, you can plug that into the calculator if you want an exact answer, but that's going to be the most simplified form there. Now, in red, let's go ahead and find our second root. It's going to start off the same way. We're going to start with the cubed root of 10, all right? And then CIS, and then what's inside those trig functions is going to be 165 over 3 plus 360 times 1 over 3. So this time we're not getting rid of that second term. We're going to consider it into our arithmetic here, and that should simplify to the cubed root of 10, the cubed root of 10, CIS, and then with a little bit of arithmetic, you will see that that comes out to be 175 degrees. And that is going to represent our second root. All right. So our third root, we're going to do the exact same thing again, but we're going to plug in 2 for k. And so that's going to start out with our cube root of 10 again, and then CIS 165 over 3 plus, let's see, 3, oops, didn't mean to get the eraser, 360 times 2 over 3. All right, and just simplifying what's inside the trig functions is going to give us, I believe that should give us 295 degrees. So let's see, that's going to simplify to the cube root of 10 CIS 295 degrees. And there you have it. We have the simplest version of our 3 cube roots of the complex number 10 CIS 165 degrees. All right, so that's all you have to do there. Now let's look at an example where we actually have to find the 5/5 roots of the complex number 2 root 3 plus 2i. And this time it's not in polar form. The complex number is in rectangular form, so we're going to have to recall really quickly how to convert that from rectangular form to polar form. Now, I'm not going to solve the whole problem for you. I do encourage you to download these notes and finish off where I leave off on this video, and then you can obviously check with my completed notes, which are also going to be linked below. But the way that we're going to convert this really quickly as a reminder is we're going to be looking for that r. So just as a reminder, the standard polar form for a complex number is z is equal to r times cosine theta plus I sine theta. So all we need is we need that r and we need that theta. All right, so how do we find r really quickly? So if we look at a rectangular complex number like a vector, right, with 2 components, the real component and the imaginary component, then what we're going to be looking for is we're going to be looking for the magnitude of that vector, with the real component being the one that doesn't have the I as a factor, and then the imaginary component being the one that does. And the way that we're going to find the magnitude of that vector is it's going to be based off of the Pythagorean theorem. We're going to say that r squared is equal to the square of our real part. So that's going to be 2 root 3 plus the square of our imaginary part. All right, so that one's pretty easy to just work out in your head. No need for a calculator here. That's going to be equal to 4 times 3 plus 4. Simplify that another round. That should be 16. All right, so clearly r is just 4. All right, so hopefully you followed me there. And that was pretty easy. But then how do you find theta? Well, we can talk about the trigonometry, but we are just really trying to memorize how to quickly get it from rectangular form to polar form. So what you're going to be needing to remember for that is theta is going to be found by taking the inverse tan of our imaginary part over our real part. All right, so you can plug that into the calculator really quick, or if you're just really comfortable with right triangle trigonometry, you might be able to see that that is going to be equal to 30 degrees. All right, so that's the inverse tangent of our imaginary portion over our real portion. That should give us our angle theta. All right, so that said, we now have everything we need to just go ahead and write it out in polar form, and we're going to see that z is going to be equal to 4 cosine 30 degrees plus I sine 30 degrees. All right, so now I encourage you to actually take that, go ahead and plug it into Moivre's theorem, solve it out yourself, and then check it with the finished notes that I have linked down below. All right, good luck, and I'll catch you in the next one.